Okay, the topic of today's lecture is Central Limit Theorem. Central Limit Theorem is a three-word for some fact or facts about the sampling distribution. And what I mean by that, it is in general case you are sampling from one variable. That means that you are collecting instances of one variable. So for example, if you want to collect the shoe sizes of people, then you have a variable that is the random shoe size, and then you're going to collect, depending how many you want, you're going to collect a number of instances of shoe sizes from a bunch of individuals, right? So that is your sample. Now, what you might be interested in general case, it's some kind of method of the population. You're interested in something about the population, and then you are making conclusions by using what you get in the sample, assuming that the sample is a good representative of the population, right? We talk about that in the very beginning of the course. In this story here, we are going to be talking about estimating the mean of the population, or you're trying to get some knowledge what would the mean of the population be, right? So for that reason, you will calculate the sample mean. So you're going to get the sample mean, and you think maybe this sample mean is going to be something close to the population mean. That would be the idea. Okay, so now the question is, if you collect different samples, what is this guy going to? In one sample could be one thing, and another sample could be another thing. So for example, I have here random variable is the GPA of a high school senior. So that would be a class of 30 of them, and I have the first one has 3.23, the second student has 3.11, the third student has 2.35, and on you go. And I can see the last one has here 1.98, so there are 30 of them. So you have a bunch of students with a different GPA. Some of them are good, some of them are not so good students, but you have lots of them here. But we call that large sample because it's already at 30. The number of items in the sample is 30, and that would be for us large sample. So what could I be interested in? Maybe finding an average. Well, how good is this group of students? What is an average? Average in this group is 2.79. And how you get that? Of course, you have to add all of those guys, divide with 30, and you're going to end up with 2.79. Now, if you take another group of 30 students, so I have as GPA, the third individual is GPA, and on you go. In this group of 30 students, I have somewhat lower average GPA, 2.73. Okay, and you can go on with that. You can find a third sample and fourth sample and fifth sample. I'm always using 30 because I want to have sample to be comparable, to have the same number of items, entries in the sample. So then you realize sample mean is variable. It changes from sample to sample. And now remember, I'm trying to guess what this guy is, and I know this guy is not variable. So the reason why I'm collecting samples so that I can get sample mean, and I would say, maybe that's a good estimate of the population mean. But I can see here I have another problem here, that this sample mean from one sample to another sample changes. So the question is, how? How is this guy changing? All right? And the answer to that is Central Limit Theorem. All right? So before I tell you what the Central Limit Theorem is, I want to have to tell you what the words mean. The first word says central. Okay? Now, there are two versions about it. One of them is that this is the single most important theorem in statistics, and that is true. Another one is that in the probability, this is not the most important theorem, but one of the important theorems in probability. But in probability, this is a theorem that talks about measures of central tendency. This guy, right? So that's why it's called central. The second word is limit. The word limit in our case, it means something very specific in calculus, but in our case we're going to say that this is actually an approximation theorem, which means approximation fact, which means it doesn't tell to you that A is exactly B, but it tells you that A is approximately B. And we can even figure out how good that approximation is, but it is just telling you that something is approximately something. So if I tell you there is a 80% chance tomorrow that we will have a rain, or let's say snow, I'm stating a fact, right? I'm stating a fact, but I'm not telling you tomorrow will rain. I'm not telling you that. I'm telling you there is a 90 or 80% chance that tomorrow will rain. So I'm stating a fact, but it's an approximation fact. It's not exactly what's going to happen. If I tell you tomorrow will rain, that would be a certain fact. But of course, I cannot be a certain, right? So the limit means in our understanding here, it's an approximation fact. So you have now very important approximation, and theorem means exactly that's what I just said, fact. And it's something that you can prove. So that's from a Greek word theorema, which means something you can logically explain, something that is self-provable. It's a fact, but it's a fact that can be explained, right? So those are the three words in this thing, what we call central limit theorem. So this is, again, very important approximation fact, if I want to translate that, right? So what does it say? It talks about what this guy is, right? So I already know that the sample mean changes from one sample to another and so on, and it's a random variable, and we're gonna honor that by just writing an uppercase x bar. So now we know it's a random variable. So central limit theorem tells you what kind of random variable this is. That's very important. It's not just anything, it's something very specific. Okay, so we're gonna separate the central limit theorem into two facts, the fact A and the fact B. The fact B is actually what is usually understood the central limit theorem. The fact A is just an elementary property of normal distribution, so it's not anything special. But both of those facts are so similar that I'm gonna jump them together, and I'm gonna say this is a fact A of the central limit theorem, and then we have a fact B of the central limit theorem. So you're gonna have to remember them both, unfortunately, right? Okay, so what is a fact A? Okay, if the original random variable, so you're sampling based on a particular random variable. So in this particular case, the random variable is GPA of a random high school senior. Okay, so you have 1, 2, 3, and so on. Okay, so if that original random variable, that x, GPA of high school senior, is approximately normally distributed, then the x bar is also approximately normally distributed. Okay, so again, this is not particularly difficult to understand, and it actually makes sense, but we can say a little more. We can say also this guy is on average, what is the average of the population? So it's, we can put here mean of x. So I don't know what that GPA of a high school senior is? I don't know. I just know here there is one sample mean, there's another sample mean. I don't know. Maybe you can guess 2.75. Now, I don't know what it is, but I know that number exists. There is an average of all of the GPA, high school senior GPAs. I mean, all of the GPAs of high school seniors. Okay? It also has the standard deviation. And standard deviation, we're going to label the standard deviation of x, so which means it varies from student to, of course, this is the variance. So it has a variance. So, what about this guy? So again, you have the variable, a single student, random student GPA, and then you have a mean of 30 of the students like that. Okay, and again, this varies from a student to student, this varies from a sample to sample. Both of them are variables. So if this one is normally distributed, the central limit theorem says this one is also. The question is, the first one, the x, is distributed normally as normal random variable. There is an average, and it, so we said this one, let it be normally distributed. It's normally distributed, it's going to have its mean, it's going to have its variance. So what the central limit theorem says, this guy here is also normally distributed. Okay? And it's also going to have a mean, its mean, and it's also going to have its variance. So what is the mean of this guy? Okay, let's think about it. If an average from student to student in the population, the mean GPA is 2.75. Now, if you take a class of 30, you get the average of 2.79. A class of 30, you get the average of 2.73. And on you go, another class of 30, another class of 30, another class of 30, so on. What do you expect these guys from the first class, second class, third class, so on average going to be? And the answer must be, it's going to be, again, the mean of the x. So the mean of this guy is the same as the mean of the x. They cannot be different. Okay? In other words, the mean of the means must be the mean. Okay, so that is not surprise. Okay, now, what's the variance? That's another question. What is the variance of this guy? Okay, the variance of x is, we just label it here, it's a sigma squared, population standard deviation squared. Okay, let's think about it. If you go from student to student, that's the story about the variation of x. There's going to be plenty of variation. Here is one guy has 1.98. Here's another guy who has 3.55. This is an A student. This is a barely a C student, right? Okay, let's say C student, right? So we have a C student and an A student. So there is a big difference here. And you can find more. Here's another, I don't know, it's a C minus or D plus student. And then you have another one that is a B student here. So there is a big difference between 1.64 and 3.11. This student is much better than this one here. Okay? So you expect the difference to vary quite a bit from a student to student. But when you go from a sample to sample, you got here 2.79, here you got 2.73. I don't think you expect there will be a sample of 30 students that we will have a GPA average of those 30 students to be 1.64. That's impossible. It's not going to happen. There will always be some good students there, so the GPA is going to be higher. And it's also, I don't expect it's going to be 3.55. That means that I would have 30, on average, 38 students. That's not going to happen either. So what I'm saying here is that the variation going from one sample mean to another sample mean to another sample mean is not going to vary that much as going from one student to another student. So this guy will not have the same variance as this guy. It's going to be smaller. Okay? Now, this is an important conclusion what central limit theorem says. It's central limit theorem says, I know exactly how much smaller that variance is going to be. It's going to be a fraction of this variance. Okay? What kind of fraction? Well, it gotta be related to the sample size, right? So the bigger sample size, the less variation that will be. And that's exactly the case. N times smaller. So the variation of this guy, the variance, is going to be 30 times smaller than this guy. If the sample is of size 30. If the sample has a size 200, then this guy will have a variance 200 times smaller than this guy. That is what central limit theorem says. Okay, this is very important. Okay, this fact A is very important. Okay, now I'm going to show you immediately one example of using this fact. I have the height of 18-year-old man, approximately normally distributed. We talked about it before. Has a mean of 70 inches, the mean height, and the standard deviation is 3 inches. So which means that x, the height of a random 18-year-old man, is distributed normally with the parameters. The mean is 70 and standard deviation is 3, or the variance is 9. Okay? Now, what is the chance that an 18-year-old male selected at random will be between 67 and 73 inches tall? Right. That's easy answer. The question is about the standard deviation back and forth from the mean, right? The mean is 70 and standard deviation is 3. So this is 3 or a standard deviation less than a mean. This is 3 above the mean, 70 plus 3, 73. So that's a standard deviation above the mean. So this is standard deviation back and forth from the mean. And we said that is by empirical rule 68.3%. Okay, so that's the answer. Easy. I don't need a table. It's easy to answer. Okay, now if I select a sample of 9 18-year-olds, what is the chance, the mean height of that sample? So now I have 9 of them. Each one of them is 18-year-old, and I measure the height of each one of them, and I'm going to find the average height of 9 of them. What is the chance that that is going to be between 67 and 73? Okay, now the question for you is first, what is x bar? Okay, and we just said from a central limit theorem that this guy is normally distributed. Why? Because the height is normally distributed. So x is normally distributed here. X is normally distributed, so the mean of the sample is also normally distributed. Again, it changes from sample to sample, right? Sample of 9, another sample of 9, another sample of 9. It changes. But it's distributed normally because the central limit theorem says so. If this guy is approximately normal, so is this guy. Right? That is a central limit theorem fact. But it's not the same normal, okay? It has the same mean. The mean of both of them is 70. Okay, but the variance is not the same. So we just argued that before. The variance is not the same. This one has a variance of 3 squared, which is 9. This one going to have the variance 9 times smaller. That's what the central limit theorem says. The variance is going to be 9 times smaller. Okay? So, both of them are distributed normally. The x, the height of a random student, from one student to another student to another student, is distributed normally with mean 70 and the variance 9, standard deviation 3. The x bar That's the mean of a sample of 9. That also changes from one sample, that's one mean, from another sample mean, from another sample mean. It changes, it varies from a sample to a sample. Not from an individual to an individual, from a sample to a sample. But it has the same mean as the x, 70, right? And it has a variance. Variance is going to be the sample size times smaller. The sample size of 9, it will be 9 times smaller than what x has as a variance. So that would be this 3 squared, variance of x divided with 9. And that, of course, is 1. Right? 9 divided with 9. So the question here is, what is the chance that mean of 9 18-year-olds will be between 67 and 73? If I randomly choose a sample of 9 of them, what is the chance that that mean, the average height of those 9 individuals, is going to be between 67 and 73? And the answer is again easy. Since the standard deviation, this is the variance here, that's 1. But the standard deviation is radical of square root of the variance, it's also 1. So we are really talking about 70 plus 3 times the standard deviation, 3 times 1 above, and 70 minus 3 times standard deviation below 70. Okay? So this is the empirical rule, the third part of the empirical rule. If you go 3 standard deviation back and forth, you get 99.7%. So if there is a 68% chance, a 68.3% chance that a single 18-year-old will have a height between 67 and 73, we can say it's approximately 2 out of 3. 2 out of 3 18-year-olds will be between 67 and 73 inches tall, which is 5'7" and 6'1". Okay? And you measure the average height, the chance that that average height is going to be between 67 and 73 is almost 100%. Very rarely you're going to be able to find 9 of them that the average height would not go in this interval between 67 and 73. So we found that out using empirical rule, of course, but we also use center. Okay? So that's the fact A. We're going to use that in the second example as well. But I want to tell you what the fact B of Central Limit Theorem says. Okay? Now the fact A, again, let me repeat this one more time. If the original measurement, the random variable x, is distributed approximately normally, then the mean of any sample taken out of that is also going to be approximately normally distributed. And it will have the same mean as the original one, but the variance is going to be n times smaller. Okay? The central limit theorem fact B, which is actually the central limit theorem as understood by most of the people that study probability and statistics, does not require that x is normally distributed random variable. It only requires that x be a random variable that has a mean and a standard deviation. And most of the random variables do have mean and standard deviation. So you might wonder, how is that now? Most of them. So there are some that don't have that? Yeah, there are some. But we will not meet that in practice. Those are just some theoretical pathological examples. We don't really meet them in practice. So this is assumption here that the deviation, GPA of students, will have a mean, because there will be a mean of all of the students in the United States, and there will be, if there is a population, and there will be a standard deviation. It's going to be difficult to calculate. It's going to be a huge number in that population, but you know you can find it. All right, so that's the requirement here, that we do have the mean and standard deviation. Okay, and this is about story about GPA, because GPA is generally not normally distributed. I don't believe it is, right? Nobody tells me that this must be distributed by, you know, symmetric curve density. It might be, the histogram could be something else. It might look like that, right? So I know it has to be something between 0 and 4. You can't have anything more than 4, and you can't have this GPA less than 0. Now, most of the people are going to have high school senior. Most of them are going to have a GPA, I don't know, between 2 and 4, right? But there will be some that are going to have, you know, very low GPA, might be even close to 0, somebody who is totally flunking everything. So that's the something I expect. So this is normal. This is not normal. Normal should be symmetric. This one is skewed to the left. So I don't think it's normal, right? So basically what we are talking here is that if I want to apply the central limit theorem on the situation of random apply GPAs, then I would probably have to use the central limit theorem fact B, because the fact A requires that X is normal, and I don't have it here. I don't think I have it. Okay, so what does this part of the central limit theorem say? This is the story. If X has the mean and standard deviation, then X bar again is approximately normally distributed. As long as you can get large sample, as long as the N increases, then you're gonna get this guy approximately normal. All right? So you need to have the sample at least 30. Once you have a sample of at least 30, you can claim that this guy is approximately normal. That is, you can claim that this guy, again, regardless of the nature of the original random variable. The original random variable, high school GPA, doesn't necessarily have to be normal. The only thing we ask is that it has a mean and standard deviation. But we can conclude that X is normal. And it's again, as before, it's going to be approximately normal, and it's going to have a mean the same as the original. So this is the mean of X, the same mean, and the variance is going to be the original variance n times smaller. Okay, so again, you can write X here. So this is the mean of X, and it's also the mean of X bar. This is the variance of X, and the variance of X bar is n times smaller. So this is very important conclusion, because it does not require at all that X has some kind of defined distribution. Does not require that at all. It only requires that you need to have a mean and standard deviation. So the variable has to have a variance and the mean. That's it. And as long as you can vouch a big sample, as long as you can collect a big sample, this guy is going to get this guy. The sample mean, the changes from a sample to a sample, will be normally distributed. It's going to have the mean the same as the original one, which has mean, I just wrote mu here, and the variance is going to be n times smaller than the original one. Okay, now when we do the calculation really with the normal random variable, we don't really look for the variance, we look for the standard deviation. So you really have to take a radical. So when you take the radical of this guy, so this is the variance, and you really need a standard deviation, so you take the radical. And when you take a radical of fraction, some of you know some algebra, right? you take the radical of the numerator and radical of the denominator. Radical of the numerator, this is a square, I'm taking a square root, I'm just simply going to end up with the original standard deviation. Downstairs, I don't really have anything better to do than just say I'm going to have to take the square root of n. Okay, so this is the standard deviation of x bar. So if you're looking for standard deviation of x bar, this is not the standard deviation of x, it's standard deviation of x bar. That is the standard deviation of x divided with the radical n. This is called standard error of the mean. And this term, this phrase is very often used. So when somebody says standard error of the mean, it means this. So that's the standard deviation of the original random variable, whatever that is, high school GPA or something else, divided with the radical of the sample size. Okay, so again, this is actually standard deviation of x bar, something that you're going to use in the calculations, right? So you need to know this number, whatever that number is. Okay, so, and again, if you're going to use a fact B of central limit theorem to conclude that this guy is normal or approximately normal, you will need to have a large sample. Okay, that's our rule of thumb. It might be applicable on a smaller sample, but to be safe and to be able to use this conclusion that this is really approximately normal. So notice this, from the very beginning I told you the central limit theorem says it's approximation, right? This one is approximately normal. So you need to have a large sample. And the bigger sample is, the closer this is to equal, right? If you can have a sample that is made out of infinitely many things, it's almost that's not possible. But if you would have that, then you would have this equal. This would be exactly normal. Okay, so you can count on that. So we have now fact A and fact B of central limit theorem. Again, both of them are tackling what is this guy, the sample mean that changes from a sample to a sample based on what we know about original random variable. So this is a sample mean of 30 GPAs. This is, for example, this is the single GPAs, random student GPA. So if we know something about this guy, what do we know about this guy? So again, fact A says, if this guy is normally distributed, then this guy is normally distributed. They have the same mean, only the variance of this guy is n times smaller than the variance of this guy. So that's the fact A. The fact B says, you don't need to know what is this, but you need to have mean here and a variance, standard deviation. So you need to have a standard deviation and you need to have a mean. Now once you have that and you have a large sample, then this guy again is going to be approximately normal. And it's going to have the same mean as this guy, only the variance of this guy is going to be n times smaller, the sample size times smaller. So basically, the fact A and fact B are making the same conclusion. The fact A requires this one to be normal. The fact B requires not this one to be normal. It doesn't ask for that, but it asks for a large sample. Okay, so there's a trade-off. You don't need to have this one normal, but in that case you need to have a large sample. Okay, let me give you another example. How would you use this central limit theorem? Okay, the second example says the white blood cell count per cubic millimeter of blood is approximately normal with a mean of 7,500 and standard deviation 1,750. Again, so the white blood cells are very small blood cells that are in a cubic millimeter of whole blood. A cubic millimeter is something very small. Centimeter is about 40% of an inch, and a millimeter is a tenth of a centimeter. So something very small. So talking about a very small cube. cubic millimeter, excuse me. So we're talking about a very small cube, okay, of the whole blood. And in there you're gonna find something you can see, but you can see with the microscope, 7,500 on average white blood cells. And the standard deviation is going to vary from individual to individual. It's going to be 1750. Quite a bit of a variation. Okay? Now, if a doctor uses 2 test average, so it gives you 1 blood test and then do that again, what is the chance the 2 test average is going to be below 4,500? So now I would consider it to be kind of low. Right? So he might be interested in that. People usually have a low blood cell count, white blood cell count, if they have AIDS. So that's usually a consequence of HIV infection. All right, so something that you want to know, right? So what is the chance that this is going to be the case? The X bar is below 4,500, all right? So what do we know? Well, we know that X, a single blood test count of white blood cells, is approximately normal. The problem says so. It's approximately normal. And it has the mean of 7,500. Okay, so you can say, oh, this is a count. How can that be normal when it's a count? And again, well, nobody really counts blood cells. We just estimate that based on density or the weight. And plus, of course, white blood cells from one to another, there's a whole bunch of different white blood cells. Some of them are bigger, some of them are smaller. So basically, it's really not a count. You can estimate as approximate normal. So it's distributed as approximately normal, as the mean of 7,500, and the standard deviation of 1750, which means the variance is the square of that, 1750 squared. You can multiply that to find out what it is. Now that's the case here. Fact A of Central Limit Theorem says what? That X bar is also approximately normal. Again, this guy is approximate normal, this guy is approximate normal. This is the average of 2, the 2 test average. Okay, that's a sample mean of 2. There are 2 items in the sample. And the Central Limit Theorem fact A says this is distributed normally. What is the mean? The same as this guy. The same as X. They have the same mean. The mean of X bar and the mean of X, the expectation of the X bar and the expectation of X is the same. The variance though, so the original variance is 1750 squared. Ought to be 2 times smaller now. So the variance of X bar is 2 times smaller than the variance of original. X is a single white blood cell count. X bar is the average of 2. So therefore the variance is going to be 2 times smaller. Okay, that's all there is to it. We only need to know this part here. Now, okay, the standard deviation is going to be the square root of this, the standard error of the mean. You take the square root on the top, you're going to have a 1750, and on the bottom you take the square root, you're going to have a square root of 2. Okay? And so what do we know? The question is, what is the chance you're going to have this low white blood cell count even if you take 2 tests? Right? So that's a question about this guy. You can answer that question by using the calculator. It's just straightforward using calculator, which is going to be by using the normal distribution. So I'm going to have selection of normal distribution, CDF. Lower bound, you don't have a lower bound, says here just lower than 4,500. So we can use, I don't know, negative 10,000. You cannot have negative 10,000 white blood cell, but it's just theoretical value because I don't have a lower bound. You can say, why don't you just use 0? Well, you can use 0, but it has to be at least 5 times below the mean, which is 7,500, right? So I can use 0. It's not that bad, but I'm gonna use negative 10,000 because I'm not gonna calculate anything, and my calculator will calculate everything. The upper bound is 4,500. The mean is 7,500. The mean of the random variable. I'm talking about this guy. Mean of x bar. Right? Mean of x bar is 7,500. And the last thing I need is standard deviation. Standard deviation of this guy is the radical of this thing here. So when you take the radical of this guy here, you get what I said before, standard error of the mean. So you take the radical of this, you end up with square root of this is just 1750. So that's a sigma. And the bottom you take a radical. Radical of 2 is radical of the sample size, 2. Okay? So we called that moments ago standard error of the mean. Okay? So you have to use that. So now I'm still working on my calculator. I need to write that number here. You can just simply write 1750, divide that, and I have the radical 2. And you have to close parentheses also. That's 1750 divided by radical 2. I'll paste. And I get, this is less than 1%, 0.00766, so you can say 0.008, right? I use 0.0078, which is also, I should actually have here 77, right? But I use the tables here, so I'm going to show you that in a moment. So I get slightly different. This one is 0.0077 as approximation with 4 decimals. This one is 0.0078. Slight difference. This is in a percent of a 1% difference. Okay, because of the tables. I'm going to show you that in a moment. So that's a calculator calculation. Here I have the table calculation because I did not use the calculator here. I used the table calculation, which is turn this one into z-value, turn this one into z-value. How do you turn 4,500 into z-value? Well, you subtract the mean, which is 1750, 7,500. You subtract the mean, which is 7,500, and you divide with the standard deviation. So the standard deviation of this is a variance, is standard error of the mean. So I'm dividing standard error of the mean, which is a standard deviation of this guy, right? So now, calculating this thing here, you end up with the approximately negative 2.42. Check it out. You can use your calculator, or you can do it by hand, but you need to find the radical here, divide 1750 with radical. This is actually 1.41142, something like that. And then you divide this guy with that, and then you subtract this, you're gonna get something negative, and then you divide with whatever you calculate on the bottom, and I ended up with negative 2.42. Negative 2.42, and now you look at the tail, we are talking about the z being below that. So it's a left tail up to the negative 2.42 in normal tables. Negative 2.42 is the number I'm looking for. 0.00878. Exactly. Okay? So again, the calculator calculation makes a difference. You get actually here, if you approximate, it's 0.0077. So it's a difference of 1% over 1%, which is not much of a difference. In either case, it's less than 1%. Okay? So if you take a random 2 tests with the white blood cell count, the average is very unlikely to be below 4,500. It's less than 1% chance that that's going to happen, according to our calculation. And again, we use here Central Limit Theorem, fact A, because we had the X, the white blood cell count, to be normally distributed, with mean 7,500 and the variance 70/50 squared. And we concluded that by the fact B, the average of 2 white blood cell counts will be also normally distributed, approximately normally distributed, with the same mean. They have the same mean, 7,500. Only this one will have a variance that is a half of this variance. Why? Because that's the sample size, 2. So you need to divide with 2. That's what the fact A of the Central Limit Theorem says. Now, I'm going to stop here, this first part, and I'm going to ask you to watch the video for the second part, starting with the example 3 here. I have a few examples here, and I also have the last example is using the fact B of Central Limit Theorem. And then I have a little story here on how you can notice Central Limit Theorem working even when you're not using a large sample, when you're using only a sample of 3, and still you can see the Central Limit Theorem working. Okay? So again, I'm going to ask you to watch the second part here, or read. All right? So that's my story for this first part.